We've seen how to calculate a least squares regression line using a calculator and by using formulas for the slope and y-intercept. A third way, and almost certain to be somewhere on an AP exam, is to grab information shared in a computer printout. Here's the basic format of a computer printout. Later in the course we'll understand and use the last three columns, but for now we don't. All we need is the column of coefficients. b sub 1 is the coefficient in front of the x variable, therefore it's the slope. b sub 0 is the constant term. Grab those and substitute them into the LSR equation and you're done. Typically we would be supplied additional information just below the table in the computer printout. Though the printout may use capital N, it's actually lowercase n, which is the number of ordered pairs in the data set, usually the sample size, though not all linear regression models require a sample. The coefficient of determination is given. One can take the square root to know the correlation coefficient r, and S is the standard deviation of residuals. Suppose we're testing to determine if a drug was effective in lowering cholesterol in patients suffering from high cholesterol. We randomly assigned similar patients a dose of medicine to take for 4 months, and then measured the cholesterol levels at the end of 4 months. Here's the computer printout. Use it to answer some questions. There is much we can know from this. First, notice that milligrams is under the constant. This alerts us to the fact that the x variable is milligrams of the dose of the drug. And predicting the cholesterol level as a result is what the LSR line will do. Thus the y variable is the cholesterol level. The y-intercept is 267.2, therefore a typical cholesterol level for the patients in this study prior to taking the drug was about 267. The LSR line is y hat equals 267.2 minus 0.44x. We can interpret this slope by saying for each additional milligram of drug given, the cholesterol level tended to decrease by 0.44 points. If a problem asked us to predict the cholesterol for someone who took 30 milligrams of the drug, we would substitute 30 for x and arrive at a prediction of 254. N equals 28 participants, r squared is 0.535, therefore 53.5% of the variation in cholesterol level is explained by the linear relationship to the dose of medicine given. The correlation coefficient is the square root of 0.535, but is it the positive or negative square root? Well, the slope answers this question. We have a negative slope and thus a negative linear association. Therefore, r equals negative 0.731. S is 7.1 points. So using the rule of 68, 95, 99.7%, we would state that around 68% of observed cholesterol levels should be within 7.1 points of the predicted cholesterol level obtained by using the LSR line. Finally, despite possible high r-squared values, we should always be in the habit of checking a residual plot or scatter plot to verify linearity, consistency of variance, and normality of residuals. Often on the AP, they'll simply say an examination of the residual plot revealed no concern with regard to these assumptions.